Welcome to episode 14 of CipherVibe's end-to-end cloud security architecture course. Encryption protects confidentiality for stored and moving data, but depends on key ownership and verified enforcement across all paths. We will connect its purpose, design boundaries, implementation path, failure modes, and evidence of effectiveness. Every cloud security layer relies on the ones around it. Encryption consumes classified data requirements and key services while supporting network security, workload hardening, DLP, compliance, and incident response. It must be paired with access control because encryption does not decide who may use decrypted data. Treat the architecture as a chain. A trusted identity requests an action, a policy makes a decision, a workload or data service enforces it, and telemetry records enough context to investigate later. The first building block is protect data in transit. Use modern TLS configurations for public and internal service connections, validate certificates and host names, disable weak protocol and cipher options, and automate certificate renewal. Include service-to-service traffic, administration, replication, and backups, not only the customer-facing website. The second building block is encrypt storage by default. Enable encryption by default for object storage, disks, file systems, database storage, snapshots, logs, and backups. Verify how encryption applies to new and existing data, copies, replication, and exports. Choose key models based on sensitivity, operations, and regulatory commitments. The third building block is use application layer protection where necessary. For particularly sensitive values, consider field-level or cell-level encryption, tokenization, or masking before the data reaches a broad platform layer. Design for search, analytics, backup, rotation, and support workflows so application layer protection does not become an unusable or unmaintainable secret system. The fourth building block is treat certificates and keys as live assets. Inventory certificates and their owners, automate renewal, protect private keys, monitor expiration, and rehearse revocation. Encryption fails operationally when an expired certificate causes emergency bypasses or a rotated key makes data unavailable without an understood recovery process. Use this reference pattern. Begin with an explicit policy that describes the permitted outcome. Enforce that policy at the closest reliable control point. Route decision and activity evidence to protected storage. Then give an accountable team a tested path to review exceptions, correct drift, and respond to violations. A complete encryption pattern protects every data path with validated transport, encrypts every persistent copy by default, adds application layer safeguards for selected values, and operates keys and certificates as controlled assets. Implement this layer in a sequence that preserves evidence and limits blast radius. First, map data flows and copies for a priority application second, enforce modern TLS, and automate certificate lifecycle third, enable and verify storage and backup encryption fourth. Identify fields that need tokenization or application layer encryption fifth, test rotation, restore, and client failure behavior prefer pilots with a named owner and rollback plan over an unmeasured organization-wide switch. The best rollout is one where a normal workflow succeeds, an unsafe path fails closed, and the team can explain the decision from logs rather than intuition. Security architecture fails most often through assumptions, not dramatic movie-style attacks. First, encrypting a database while leaving exports or backups unprotected second, accepting invalid certificates for convenience third, treating provider encryption as a complete access control solution fourth, rotating keys without testing application and restore dependencies. A configuration screen is not assurance. Collect evidence that the intended control applies to the correct scope and that violations become visible. First, measure TLS, storage, and backup encryption coverage second, test certificate renewal and failure handling paths third, verify snapshots, replicas, and exports follow required key policy fourth. Review cipher configuration and key use logs for sensitive services test both normal activity and a safe negative case in an authorized environment. Record the expected decision, the evidence location, the owner who reviews exceptions, and the rollback method. Repeat after platform changes, new integrations, or major shifts in business use. For a practical exercise, design encryption controls for a fictional healthcare booking service from browser to application, database, backups, and analytics export. Use synthetic information or an environment you own or are explicitly authorized to administer. Deliver a one-page diagram, a concise control statement, a list of expected audit events, and one test for an allowed path plus one test for a denied path. This artifact is more valuable than a screenshot because it explains the reasoning behind the configuration. Before scaling this layer, ask 5 review questions. Which assets, identities, or environments are in scope? Who owns the desired state and exception decisions? Which enforcement point can reliably apply the rule? Which records prove the decision and retain enough context for an investigation? And how can the organization revoke access, contain impact, or roll back safely when a control fails? Good architecture makes these answers explicit and testable. The key lesson is that encryption at rest and in transit becomes dependable only when design, policy, enforcement, evidence, and ownership move together. Document the decisions you make, remove permissions and exposure that do not support a real requirement, and rehearse the paths that matter before an incident forces the lesson. Continue through the next episode to connect this control layer to the rest of the CipherVibe cloud security architecture.